All right, let's move to our next speaker. I think you'll enjoy what he has to say. Dr. John Smee, Vice President of Engineering at Qualcomm. He is currently the 5G Project Engineering Lead in Qualcomm's Wireless Research and Development Group. His work involves taking advanced system designs and signal processing techniques from theory through design, through simulation, to standardization and actual implementation of the product. So, ladies and gentlemen, let me introduce and please provide a warm welcome for John Smee. John?
Thank you very much. Yeah. All right. Well, it's certainly my pleasure to talk to the CCA community and to talk about what is the 5G technology, where is LTE today, where is LTE going, what's the timeline for 5G. So if we look back 5 years ago, everyone's saying, hey, 5G is 2020. We don't really know what it is, but it's the next big G. They happen in 10-year increments. Well, here we want to take this time to go over some of the technical capabilities of 5G and how is it serving, different use cases beyond mobile broadband into IoT aspects like mission-critical communications. So thanks again for the opportunity for the speaking, and I'm certainly happy to take any questions at the end. So if we look at 5G NR, making it a commercial reality, what are the use cases it's serving? So this is just a sampling of where multimedia is going today, where is next generation mobile broadband. It's important to remember that when LTE was designed, everyone was walking around with silver flip phones and pretty excited about it. But the reality was the decade of LTE since then has been a significant explosion in the way people use their devices. And the other thing to keep in mind then, as we look at the next decade, the explosion of device types and use cases is also going to continue. So 5G is going to lay that continued foundation. So we look at more user-generated content. Think of congested environments. How do people use their devices today in sporting events versus what they were doing 10 years ago? Look at high-speed mobility, so the expectations that consumers have when they're using their devices on the road in a wide variety of mobility scenarios. And cloud-connected computing, in terms of what's on the device, what's in the cloud, the use of much more data that's being basically translated between the device and the network on a much higher speed basis. And in looking at immersive user experiences, we're in the early days, obviously, of head-mounted displays and new, basically, AR, VR applications. But those will be coming into mainstream in 3 to 4 years from now and achieve it, in our opinion, even more significant volumes after that. And connected vehicles is another key area where cellular is continuing to offer higher data rates, lower latency, and more advanced services. Not to mention augmented reality, where what people are seeing through their glasses is augmented with pertinent real-time information. And so 5G is trying to address this multitude of next-generation mobile broadband experiences, even as LTE is evolving today to address many of them in the near term. So if you look at, well, what do the consumers want? What are they excited about in 5G? So after some extensive survey work that we've done jointly with Nokia, there was a lot of discussions of, well, what would people want? And one of the key points was faster connectivity. So that's kind of a no-brainer. But the other thing is, will they likely purchase a new 5G phone? 50% says, yes, we want to buy that new device when it comes out. And what are the reasons? So there's the ever faster speed. There's the quicker response time. So it's important to remember that even as we talk about higher and higher data rates, latency is the other key metric that's getting improved over time. And so lower latency brings in a wider type of services. And the other thing is more cost-effective data plans. There's an evolution in how these services can be priced as the amount of data transfer, the volume of that, as we bring more spectrum online, can really change the economics. And in addition now, if we look at the mobile ecosystem, where are things going beyond the smartphone? So we look at automotive ecosystem. We look at the factory aspects. What's going on now with autonomous manufacturing? What's going on with smartwatches and remote access to healthcare? Smarter agriculture. If we look at wide area services, we talk of the rural environments where the ability to propagate longer and farther based on spectrum use enables then a wider amount of technology to be deployed in these agricultural contexts. We look at digitized logistics and retail. So the amount of data that's being part of a consumer transaction, how is that being facilitated, today with mobile smart pay? Where is that going to evolve going forward as well? Sustainable cities and infrastructure, and public safety and security. So we feel all of these different aspects are also being addressed by the growing 5G ecosystem. If we look at then, okay, where is the timeline? I mentioned earlier, we said, hey, 4G was 2010, 3G was 2000, so 5G is about 2020. Well, that's about right, and basically from a commercial deployment standpoint, these initial deployments will be coming in 2019 and 2020. But this is work that actually started in the standards process in 3GPP release 14, and now we're basically halfway through release 15. So release 15 in December finished the non-standalone spec, that is when you're using the 4G LTE core with the 5G radio access network, the 5G RAN. That spec is actually already done. So infrastructure vendors, Qualcomm and many other consumer devices companies are focused on now commercializing that initial 5G standard. At the same time, the standard body is continuing to address new functionality with the next-gen core as we speak. That's happening right now, concluding in about June or September. And then that paves the way for release 16. So we're in release 15 now. Release 16 brings a further expansion of the 5G standard across more use cases, ultra-reliable communication, looking at evolving IoT, looking at mission-critical services. So release 16 is also just going to be starting in about 3 or 4 months now, and that's also going to be addressing then shared spectrum, unlicensed spectrum, and a wider number of use cases, and that's going to continue this evolution beyond release 15 into 16, 17, et cetera. So if we look at, well, where does LTE Advanced fit into this? And the answer is that LTE Advanced is not getting ripped out to put in 5G. So LTE Advanced lays the foundation for what's going to come with 5G. So we have ubiquitous LTE in many markets today, and we look at 5G NR coming in mid-band spectrum, in low spectrum, and then also in millimeter wave. So we look at low, mid, and high spectrum opportunities for 5G, and they each have their unique propagation characteristics, which means it's a slightly different deployment methodology, but the ability to reuse those LTE cell sites to put in 5G radio equipment is going to be one of the key cost-effective aspects to making 5G a faster rollout. And so this is something where an LTE Advanced Pro accelerates that 5G deployment because you already have a lot of the infrastructure in terms of the communication, the backhaul, the fiber communications. So there's going to be an evolution of the core network. There's going to be obviously additional RAN equipment, but the two, 4G and 5G, can work very well together across a range of services. And so if you look even at the expansion that's been occurring in LTE, whether it's cellular V2X for communication between vehicles and between vehicles and the access network, we also see eMTC and NB-IoT. If you look at the IoT communities and that growing ecosystem, that's also going to pave right into 5G. 5G is looking at, hey, how can we do even better, and at the same time leverage all those investments that are ongoing now in eMTC and NB-IoT. So there's really a combined evolution of LTE and at 5G at the same time. So the fact that 5G's come into the standards roadmap doesn't mean that the 3GPP community stops evolving LTE. So you have this dual aspect of LTE is continuing to evolve, and at the same time 5G is being designed to make sure it interworks very effectively with LTE. And so another good point to make is where are we at with LTE data rates? And so the reality is LTE, it might have launched with 100 megabits per second in the very initial Cat3 devices, but the peak rate now are achieving 2 gigabits per second on LTE using license-assisted access. So the ability for more operators to offer higher data rates, leveraging a mix of licensed spectrum and unlicensed spectrum, was a key outcome in the 3GPP standardization and evolution of LTE with the technology called license-assisted access. That's also going to continue into 5G with the new radio shared spectrum discussions for techniques to basically enable further use of cellular technologies in a wider range of spectrum. And so that, as I mentioned, that LTE infrastructure then enables the 5G NR deployment. You can reuse those cell sites both for millimeter wave and for sub-6, bringing in new technologies like massive MIMO and wide area deployments. So if we look at LTE IoT, so this is a service that's starting now. There's a wider type of number of devices coming on market. Qualcomm obviously have chipsets capable for eMTC and NB-IoT, eGPRS. So this is a market that we want to ensure can continue growing even as 5G is being designed. And that's why the evolution of 5G is something that's happening in the standards body that's making sure that the 4G LTE deployments can also continue to evolve and offer long-term, cost-effective deployment models. So 5G NR IoT would enable further expansion beyond where we're at with LTE, and at the same time, eMTC and NB-IoT will continue to evolve. So this is a huge growth market beyond smartphones, beyond where we are today. So it's important to think that as we're looking forward 10 years from now, that the work that's ongoing now enables that continued leverage of all these investments that are being made across the device community, across a large number of operators looking at interesting business cases. This is about a larger number of businesses thinking, hey, how can I use wireless? How can I use advanced sensor data? Where can I expand my business opportunity? So this IoT is a key part of both 4G evolution and 5G new radio. And the other aspect is private LTE networks. If we look at industrial IoT, so we've been doing a lot of discussions with factory owners and businesses in the automation sector, and how do they see the ability to use wireless. So if we look at where they're at now, where they're going to be 3 years from now, where they're going to be 10 years from now, there's this continued investment now in saying, hey, how can we better have faster configuring factories? How can we have more ultra-reliable, low-latency communication? How can the workforce that's part of those factories have better access to data, better training, and better responsiveness in terms of the equipment? And so this aspect of industrial IoT is also a key target effort across 4G evolution and 5G. And so this is something where, whether it's time-sensitive networking or even mmWave for extreme mobile broadband, there's a huge focus on, hey, making sure not only are the consumer markets addressed, but at the same time, how can we all work together to ensure an expansion into some of the industrial markets where they could also very effectively leverage wireless communications. And as we look at what are the technology underpinnings, how is 5G different than 4G? So one of the key points is that there's a target of mission-critical services, ultra-reliable, low-latency communication. So achieving reliability at a latency bound. And so what are the key techniques that enable those two to be designed together? So 4G, you could say that in its early days was trying to make a better mobile broadband. It was trying to do better than 3G did for a similar use case. It did OFDM, it did MIMO, it did a variety of things that made LTE Release 8 a key, basically improvement over HSPA at the time. But the reality is 5G is being designed in a more heterogeneous ecosystem. So a lot of the design focus is on, well, what are the different techniques we can bring together to enable us to address these wider use cases? And so this is where we're looking at, mobile broadband. How can we get beyond where we are today? As I mentioned, if we're already at 2 gigabits per second in LTE, that's pretty compelling. So what are the further techniques that enable 5G to address an even broader range of services? That's where mmWave spectrum comes in. Access to hundreds of megahertz of spectrum, new spatial steering techniques. So mmWave goes hand in hand with antenna beamforming and advanced array processing at the infrastructure side, as well as multiple antennas in the device. Those sort of techniques work together to have fast beam searching and beam tracking to enable mmWave to address even wider mobile broadband use cases. Or obviously massive MIMO is also happening in 4G, where the multiple antennas with active RF arrays are happening in LTE, but 5G is being designed with that technology from the start. So the techniques that enable the 5G design and standard to efficiently leverage the multiple spatial streams is part of the whole underpinnings of it. And the other thing, as I mentioned, massive Internet of Things. So as the wide area, low power sensor market is being well addressed by the evolution of LTE, at the same time, we want to ensure that in the 5G ecosystem, we can even further expand to wider area services, to higher data rates, to lower latencies. So basically taking a step up over where NB-IoT and eMTC are today, even as those markets continue to evolve and that equipment operates for a very long time. So if we look at 5G overall, when it was started in the regulatory process maybe 4 or 5 years ago, a lot of the discussions were what should it achieve? So these numbers along the bottom were the agreed IMT 2020 target values for 5G relative to 4G. And so a 10x decrease in end-to-end latency, a 10x increase in user experience throughput, spectrum efficiency going up by a factor of 3. Look at traffic capacity also increasing, network efficiency. If we look at power consumption on the network side, that's something that's really been invoked into the standard. We want to ensure that cell towers, what are they radiating at 3 in the morning versus what are they radiating at 5 p.m. or in a super dense multi-user scenario? The answer is we want to make sure there's adaptivity on the network side. So the whole overall transmission approach between the base station and the device is substantially changing to make sure there's a focus on energy efficiency as well. So then we look at the spectrum side. So I mentioned, yes, there's an evolution to diverse services. So not only mobile broadband, but also the massive Internet of Things and mission-critical services. So we can think of those as kind of 3 corners of a triangle, those additional service types. And so the reality is 5G is being designed across a range of those new services. The other challenge is it's being designed across a much wider range of frequency bands. So not only the low bands, the FDD bands below 1 gigahertz, the mid-band TDD bands. So for example, whether it's China or Korea or Japan, there's a lot of focus on mid-band spectrum between 3.3 and 5.0 gigahertz. In Europe as well, and hence a lot of active discussion in the United States on, hey, what is the US going to do for its mid-band TDD spectrum? So a lot of discussion obviously in Washington and also with all the operators as they're looking at the opportunity to deploy 5G and R in mid-band spectrum. And the other part, of course, is the high-frequency millimeter wave bands, where there's significant interest in many markets, not only the US and Japan and Korea, but over time in Europe and China as well, for millimeter wave spectrum to be put to use for 5G. So it has unique propagation characteristics, but it has such a wide amount of bandwidth and data rate capabilities that it's another key aspect. So you have low, mid, and high band spectrum. And the other part then is the diverse deployments. So we mentioned 3 types of services, 3 types of spectrum, where there's a larger number of deployment topologies. So it's not just a single macro cell network in terms of the deployment topology. So the distance between the cell sites, we're going to have a mixture of high-powered macro cells and micro cells, and also self-deployable, lower-cost small cells. So the ability for different sides of RAN to work together, for network virtualization to lower the cost of equipment on the infrastructure side. If we look at the core network evolution for service slicing, the next-gen core relative to the LTE core. So a lot of it is about how can we make 5G more cost-effective to deploy. So as everyone was getting together to kick off 5G globally, there was a lot of discussions that I participated in and many others as well, to what are the real targets? And one of them was economic. It wasn't simply that, yes, of course, we're going to go higher data rate and lower latency, but the other thing was how can we decrease the cost of deployment, making sure that these additional frequency bands can be deployed in a cost-effective way. How can we ensure the cost structure on the RAN side, the core side, and the operating side can be decreased? And we also then look at service slicing. So the ability for an operator to offer many different types of services beyond the existing mobile broadband consumer data plan. What are some different ways that the network can provision service to a wider range of device types in a flexible way? So that's the diverse deployments aspect. So this is where the 5G was addressing a wider complex set of situations than 4G was when it was initially designed. And so on the millimeter wave front, I mentioned the challenge of this high frequency propagation and what it means. And to overcome that propagation, you need multiple antennas in the device and on the network. And this is something that Qualcomm's invested heavily in, and is something we're very confident is going to hit commercial smartphones in 2019 because of that aspect of the RFIC, the integrated circuits to do the antenna switching and the multiple antennas in a small device form factor. So this is something where not only do we have 60 gigahertz proof of concept commercial form factors already today, we also now have a millimeter wave prototype system and a trial reference design that we're going to be using for multiple millimeter wave trials with many operators globally. So millimeter wave is something that people didn't think was going to be feasible to put in a smartphone 5 years ago. And if we look at the technology evolution, what's happened on the silicon side and the RF side in the last 3 to 4 years, this is something where now millimeter wave in a smartphone, in a network, is one of the reasons that the FCC has been so active in looking at how they can basically enable more millimeter wave spectrum to be put to commercial use. And so if we look at what are the capacity gains of LTE relative to 5G, so the ability for 5G offering, say, 100 megahertz of spectrum, will be a key allocation as an example in Europe where they're focusing on 3.5 gigahertz, having 100 megahertz in this example, the ability to offer that median burst rate user improvement, and then also the cell edge. I think we all know that in cellular communications, the new services come not only when the highest data rate increases, but also when the overall data rate across the network raises. So that when that cell edge user has a significantly different user experience relative to before, and you're addressing, say, 95% of the user population or more in a given deployment, that's when new services and new apps start leveraging the unique capabilities of that. So the importance to raise the cell edge performance across the cell, at the cell boundaries to improve the coverage and reliability. So that's a key part of the 5G and R work, not only in the low FDD bands, but then also in the mid-band spectrum. And we look at millimeter wave, one of the key points is the ability to serve outdoor users, leveraging those LTE cell sites that are already there today. So if we look at some extensive capacity and coverage modeling we've been doing, looking at specific cell locations in the city of San Francisco and then adding 5G millimeter wave cell sites to those locations, we can also see here significant outdoor coverage, greater than 65% of users covered, and even data rates above 1 gigabits per second for more than half of those users. So this is where millimeter wave spectrum for key outdoor markets, in addition to indoor, it does not propagate well from outdoor to indoor. I think that's well known from physics, but the ability to have millimeter wave offer a substantially higher data rates, both outdoor and indoor. So then we put it all together and we look at where we're at with mobile broadband today with LTE. We talk of 2 gigabits per second today and how 5G NR is going to enable even higher data rates. The key point is this 5G NR, this is just the first step. This is release 15, and beyond this is further expansion even in the 5G system as well as LTE evolution. So 5G and 4G are going to work together to continue to evolve for an even richer wireless technology opportunity. And so this is where techniques well beyond mobile broadband come into play. So thank you very much. It's certainly been my pleasure to address this audience, and thank you for your time.
Thank you, John. Very comprehensive presentation of some very complicated, intricate issues that we have to address. Thank you so very much. And now,